So thank you, Jean-François, and thank you, Romain, for these presentations. I will be talking about the analog forecasting methods, which have already been introduced. It will give some more insights. Okay. First of all, what is an analog? I guess you start to understand it now, but it comes from the idea that for many systems, including the atmospheric system, you have recurrences. So the weather that you see on a given date is very likely to have been seen already in the past up to a small difference. So here, for instance, this is the pressure situation in 1st of November 2014, and you can see that the pressure situation in 1987 and the 4th of September was very similar. Okay, so that's a fact. And one way to use it is to look at atmospheric predictability. I can talk more about it if you want in the question session. And in the past, let's say before numerical weather prediction became very powerful in the 70s and the 80s, analogues were also used to make real forecasts, and especially there has been some debate whether analogues have been used for the D-Day invasion forecast. We can talk about it in more details again if you want. So that's analogues in meteorology, but also it's maybe a more fundamental mathematical aspect of dynamical systems, this idea of recurrence. And so it's I have more worked on this maybe let's say more mathematical and theoretical part, but I will try to illustrate what I will show you using pictures from real world examples. Okay. So how can analogues be used? Well, there are many possible ways to use them. One is downscaling and emulation, and you've seen an example in the previous talk by Romain Husson. Another way is to try to gain information on the system, and we'll see that in the first part. And another one is short-term forecast, which we'll introduce in the second part. And there are many other applications, but we can talk about it later if you want. Just so you know, what are the main advantages and limitations to me? The main advantages is that it has a low computational cost. It's fast to do a search of nearest neighbors, as Romain has shown you with KD tree methods. And it's interpretable. It's easy to understand when your analog method is failing and when it's successful. And maybe two main limitations is that it's memory consuming. You have to have always on your computer all your database stored, and you have to be able to go and pick for the closest situation in your database at all time. And also it might fail for a high dimensional system, and we'll see what I mean in more details later. Now, my personal contribution, my personal work was very theoretical, as I said, but I will try to give you some ideas of what it means in the real world. And so the first part is about the chance to find analogs, and the second part is about the reliability of analog forecasts. So on the chance to find analogs, the question that I'll try to answer is the following. If I have 10 years of data, how close will my analogs be? Because that's the question that people usually ask. And you'll see that the answer is not so easy. So I'll show you an example. I'll take the same query, the same target as I've shown before. So this is, we have a low pressure system over Iceland, quite high pressure in the north around the Azores. So it's a very typical wind situation that is bringing wind from the west, from the ocean, onto these coasts here. So it's a very interesting situation for wind energy. And Okay, so that's our target, and we're trying to find similar situations to this target. Now, assume that we are using data from 1950 to 1960. So we're searching for the closest situations between 1950 and 1960 to this atmospheric pressure situation. And these are the three closest that we find. You can see that it's fairly, the situation is fairly well reproduced. You still have a low pressure system over Iceland and a high pressure system in the south. Maybe the high pressure here is not exactly at the same place as it was here, so the wind will not have exactly the same direction, but it's fairly reproduced. Okay, and what I will focus on is what we use to estimate the reproducibility, as Romain introduced before, between these fields is the distance, is the Euclidean distance. And if you take it and you can transform it into an average pixel-wise distance, so it's in hectopascals. So you have an average distance of 5 hectopascals, 4.79 to be more precise, between these two images, between this target and the closest analog. And for the second closest, the average pixel-wise distance is 5.03 hectopascals. For the third one, it's 5.24. So it's growing, of course, by definition. And now look what happens if we're using data from 1960 to 1970. So just, it's still 10 years of data, but not starting at the same date. So these are the three best analogs that we can find of using the same target. So it's a bit slightly different situation again. And if you look at the average distance, it's a bit different. It seems to be a bit lower than what we had before, but still growing, of course, and still the same order of magnitude. And if we take again a new data set of 10 years, but starting in 1970, we find again different analog situations. The position of the low pressure system is not exactly the same, etc. So there are many differences, and here we find slightly higher average pixel-wise distance. And the question I've been trying to ask is how can we characterize these numbers here? Can we know how much, because we can see that they vary, and can we know how much they vary when we change the data set, but still keeping 10 years of data, and how much they vary when you go from the first to the second to the third analog? Okay, so we found a theoretical answer to this question, and so RK is the kth analog to target distance, where K is the analog rank. So what I've shown you here, this is R1, this is R2, and this is R3. So you can see that they all vary. R1 does not always have the same value. So that's why we are showing here an average, and here we're showing a standard deviation. But I will focus mostly on the average. So here, the first part tells you that the size of your catalog, so the catalog is the data set that you're using. So here L is 10 years. The size of the catalog is taken to the power 1 over D, where D is the dimension. So that means that the size of the catalog that you need for a given analog precision grows exponentially with the dimension. So if that's what Romain Husson said before, he said that when looking for SEMWF wind maps, he found more reproducible wind maps, so better analogs when there were less different weather regimes. So that means that if what you're looking at is less complex, you will find better analogs. So that's really what this part of the formula says. It says the higher the complexity of what you're trying to search analogs from, the farther will be your analogs. And this tells you how RK grows with K. And basically, it grows as K to the power 1 over D, where D is the dimension. So in high dimension, it grows very slowly. and in low dimension it grows very fast. Okay, and here this is an example that shows that using this data of pressure and doing exactly what I've shown you, we can see that our theory for these two formula does fit the data set, the data that we find. We find indeed a slow growth of RK with K. So that comes with the idea of a fairly high dimension of 12.8. So that's what I said, that we can use analogues to infer properties of the system we're looking at. Here, just by looking at the data, we know that the dimension is 12.8. So that would mean that you would need at least 13 measurements to be able to reconstruct the pressure field. So if you're thinking of placing sensors, as you will hear in the following talks, this would tell you that you would need at least 13 sensors to be able to reconstruct the pressure field. Okay, and we also see that the variability here for the first analog is higher than the variability for the 50th analog, and that is also consistent with our theory. Okay, excuse me, I was a bit fast. Now I am switching to my second part, and this is about analog forecasting. And I will not show you the theoretical results that I've proved. We can talk about it later if you want, but I prefer to show you one example of trying to use analog to make a forecast and how it works. So we've seen that we can find analogs that are close to the present, but the question is, if you're using their successors, will they stay close to the future, and can you use that to make a forecast? So this is an example for wind. This is the coast of Brittany. So here wind is coming from the southwest, and the intensity is between 5 knots here, 15 knots here, 10 knots, 15 knots, and 5 knots. Okay, and so this is what I call the present from 27th of December to 2019. And these are the 3 best analogs that we can find in a 5-year database from the Rome model reanalysis. And you can see that again, we're quite able to find good analogs. The wind situation is fairly well reproduced. And now the question is, if you look at the future, so 1 hour later at 9 a.m. at the same date, will the successors also be close to the future? And the answer is yes, but sometimes you have some issues. Actually, you have many, but I want to point out maybe these 2 here. Here, the successor number 2 had quite the same direction as the present at the bottom left of the map. But now you see that in the future it's going more to the north, and here it's going more to the east. So the direction is changing here, and also here you have a drop of intensity that you do not observe in the real future. And so one way to leverage this problem is to use averaging. If you take not just 1 or 2 or 3 analogs, but you take 40 of them and you make an average, that's the wind map that you get, and it doesn't have the issues that we've seen before. So that's one way to improve the forecast. But if you try to look at a harder problem, if you go to not a 1 hour but a 3-hour forecast, you can still do average, and it's still better than using the individual successors, which can go sometimes in very different directions. But there are still some issues. For instance, here again at the boundary, we have a wrong direction compared to the real future. So what is missing here? We're missing large-scale spatial information because, as you've seen, we have problems at the boundary. We're also missing maybe some temporal information. We're not using data. We're just using data from the present, but we can also use data from the close past. And also we're missing the seasonal and diurnal cycle. Let me show you why. Here, this analog number 1 is from May, which is a very different season than December. This one is even from June, so it's really from the summer. And this analog here is from 5 p.m. in the afternoon, while the present is 8 a.m. in the morning. So you might want to include enforce these cycles by adding more conditions when searching for analogs. And also we have a 5 years data set, which is very small. So we could either use a larger database or we could try to reduce the dimension of the problem by keeping only meaningful information. And I believe you might see some use of EOFs in the next presentation, but I'm not sure. So, but anyway, this is when you want to reduce dimension, this is problem specific. Okay. Yes, so I can come back on that. So this is about my personal work, which is more theoretical and not directly related to what I've shown, but we can come back to this in the question session if you like. So some conclusion, especially we've seen the analog to target distances, and we've seen that they can be evaluated from the dataset size and the dimension of the system. In my work, I've shown that analog forecasting errors can be explained by local dynamics of the system. We can talk more about that in the question session. You have to remember in practice to define the analogy according to your objective. As we've seen, it's what Romain was talking about also. You can try to include other variables. You can try to include large-scale information or temporal information, depending on what you want to forecast. And you have to be aware of data scarcity in high dimension. The potential applications have already been mentioned, realistic wind emulation from satellite data, as you've seen, and reconstruction and forecast of wind at farm location from partial sensors observations. And you'll hear about that a bit in the talk of Maxime Thiebaud, and we could try to use the work of Yi Chun-zen and Pierre Tandeo. Okay. Thank you. I will stop now because I am slightly over time, and I will leave the floor to the next participant.